So did any one of you try this out? Can someone tell me the answer? I want both the answer. If it is yes, why? If it is no, why? Okay. So again, let me put the question. There are two PCs connected to the two switches, as you can see, and those two PCs are connected. Not two PCs, sorry. The switches have two interfaces, right? And they both are part of access VLAN 10 on switch 1 and access VLAN 20 on switch 2. So if you do a ping from 10.0.0.1 to 10.0.0.2, will it ping or not? That's the question. So anyone would like to give a try? And I want the explanation as
It will ping, Laksh.
well. Okay.
Yes.
And why? Yeah, why?
Uh, when this frame will be generated, right?
Okay. Okay.
From
Let's talk from this perspective. If someone tells you, tell me the packet flow.
yeah,
Now
sure.
let's from that perspective. Let's start
Okay,
how this.
so a packet will be generated from PC1,
Mhm.
right? Source IP will be 10.0.1 and destination IP
Yeah.
will be 10.0.0.2.
Okay. Good.
Okay, and then it will attach. I'm assuming like this PC1 don't know the MAC address, or does it knows, right? Shall I
It knows.
explain that?
Okay. Yeah. 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 Let's
Okay,
assume it knows. Yeah.
okay. Then it will put the source IP of this machine. Source MAC will be of PC1 like 10.0.1 on layer 2 Ethernet header,
Yeah.
and
10.1.
destination MAC of 10.0.0.2. Okay,
Yeah. Okay.
this frame will come to the switch port interface, right?
Yeah.
And this switch will receive this frame. Okay, and
Mhm.
it will see that I am receiving this frame. Like this switch knows like this interface is a part of VLAN 10. So this Ethernet frame is belonging to VLAN 10. Okay,
Let me
and after,
interface number one, interface
yeah,
number two, interface number and interface number two. So
yeah,
MAC address it receives it 10.1 on port
yeah,
number one. Yeah. Okay.
yeah. So it this will see, okay, I received this frame, right? So I'm receiving it on VLAN 10, and
Hmm.
uh, and I need to forward this to since it is a part of 10, so this switch will broadcast this copy to all that interface like which are part of VLAN 10, and for this destination MAC 10.2, it is in its MAC table. It will see I am receiving this MAC from interface 2 of this switch 1.
Hold on. So it broadcasts it out of all the interfaces
All
that are part of VLAN 10, right?
right,
Right. Okay. So it is received by switch number two on interface. Yeah. Since
1.
the green ones are interface.
Yeah. So when the switch to interface like 1
Mhm.
will receive, right, since these are untagged packet, right? So switch to assume that I'm receiving this Ethernet frame, right, which is a which is to me, so it will consider like this is for VLAN 20. Okay.
Okay. Yeah.
So now this switch 2 will receive, and since this is a part of VLAN 20, so it will send a copy of this Ethernet frame to all the ports which are a part of VLAN 20.
Right.
And
Yeah.
this frame will reach
Okay. Yeah.
to
That's enough.
PC2.
That's enough. That's enough. So good one. So that's the correct explanation. And again, the return traffic would also happen the same way, where when PC2 is replying, it will have a source IP of 10.2, right? A destination IP of 10.1 on at the layer 3, right? And at the layer 2, it will have a source MAC of 10.2's MAC address and destination MAC of PC number 1, which is 10.1, right? At the layer 2. Then now what happens? It will forward the packet. Switch to receives it on interface number 2, right? So it notes down the MAC address of PC number 2. It received it on 2 and the VLAN number is 20, right? Now here, when it sees the MAC address as 10.1, it checks, does it know the MAC address of 10.1? Yes, on interface number 1. And do they belong to the same VLAN. Yes, right. So it forwards it to switch number one. And the one specific thing that he mentioned is they are not tagged. Okay. First of all, why are they not tagged? Because as I mentioned, they are access interfaces. Okay, they are access interfaces. And what does access actually mean? Access means that on that particular interface, only one VLAN can exist. It can be any VLAN. It can be from 1 to 4096. Right? It can be any VLAN from 1 to 4096. That is what access means. Right. So if on a particular port, the VLAN has been mentioned as access port VLAN 10, right? So the switch is expecting any traffic which does not have a VLAN, right? If it has a VLAN tag, okay, here what happens when switch 2 forwards it, because it has been tagged as VLAN number 20, access VLAN number 20, because it is access, it does not tag it. Why? Because it assumes whenever I am sending a particular data out of this interface, it will only be of 20 because I have been configured or this interface has been configured for access. So whatever data that is sent out or is received and does not have a VLAN tagging belongs to VLAN number 20. This is what the switch assumes. Let me again repeat. Access port means whatever data is sent out or is being received, right? It is a part of VLAN number 20. Right. So basically, it's like, let's say there is a house. Okay, there is a house, and you are the sole person, or let's say you have a security over here. You have a security guard over here. Okay, and you are the only person who lives in this house, right? And you have hired a security guy to look after this house, right? Now, this security guard knows you, right? Let's say you are VLAN number 20. This security guard knows you. So if you enter the house or if you exit the house, this security guy is not going to question you. He is not going to ask you for your ID because he knows you, because you are the sole person who is living in that house. Correct. Now let's assume instead of this being a house, let's say this is a big apartment where there are hundreds of residents living. Now this security guard, now every time a guy like anyone who is trying to enter or anyone who's trying to leave, he'll do a check. Is he a person who belongs to this apartment or not? Correct. When he is checking, when there are multiple people living in the resident in the apartment, the security guard needs to check for their ID, right? And in networking, this happens only when that interface is configured with trunk. But if it has been configured with an access interface, as an access interface, meaning that there is only one person living in this whole building or this one single house, right? The security guard is not going to ask for his ID or in networking term, VLAN number. That is why when the switch 2 here is sending out a data, it is not tagging it with any VLAN. Now, what happens when it is received by switch number 1? Right? When it is received by switch number 1, again, since it is an access port, as I said, access port meaning just one VLAN. The security guard inside the switch number 1 is not going to check for VLAN number 10 because it knows from this interface only one VLAN can come or can have an entry or can exit. And the receiving data does not have any VLAN ID. It does not contain any VLAN ID. That means, give me a minute. Okay, as I was saying, so when switch number one receives this and it does not see any VLAN, it assumes that I don't have to check for this. I don't have to check for a VLAN because there is no VLAN ID. And he is the sole person who should be entering the interface. And that is why switch one accepts the data because there is no VLAN. And it forwards the data to PC number one. The same thing happens when switch one is forwarding that data to switch number two. Switch number one is not tagging it with VLAN because, again, it is an access port. Only one VLAN ID can pass through it, and that is VLAN number 10. So what's the point of tagging it? So it forwards the data, and because there is no tagging on that interface, switch 2 assumes the data which is coming inside, right, does not have a VLAN tag, and it must be for VLAN number 20, and it accepts the data and forwards it to PC number 2. Okay, so this is why access, to be very honest, this is a kind of a loophole. Okay, it is a loophole in the your whole VLAN configurations. If you have configured access interfaces between two switches, again, please remember, between two switches. If you have configured as an access VLAN, right, and you have configured two different VLANs like this, one interface is VLAN number 10, the other interface is VLAN number 20, the two devices can talk to each other. This is a loophole, and that is why it is recommended by every vendor that if you are configuring VLANs between two switches, the two interfaces should be trunk interfaces and not access interface. All right, any question? No question? Okay.
Yeah.
And let's do a quick practical about whatever we have seen till now. It's number 2. Let me add PC number 2. PC number 4. Which anyone wants to say anything?
No.
Is the topology visible?
Yeah.
So here what I'm going to do, as we had discussed in our first session, what we did, we assumed two things. We assumed that all the PCs, they know about each other's MAC addresses. And the second assumption was the switch is completely unaware of those MAC addresses. Right? So if I want each PC to know about each other's MAC address, obviously, I'll have to ping them first. And as someone had mentioned that the moment we do this, actually what happens, a GR will be generated. I'll show you that. So 10.0.0.1. We'll talk about GRP in our later class, but let me just tell you. See here, the moment I assigned an IP address, right? So what is happening? This PC generated a GR, or called as gratuitous R, GR, right? Where basically it is telling about its own MAC address and its own IP address. Okay, so you see here, it says the outbound packet, right? It is saying it is talking its own, it's sharing its own MAC address. Also, it is sharing its own IP address, right? And it is sending it to 10.0.0.1 itself. Target IP is 10.0.0.1, and it the broadcast, and at a broadcast MAC address. So now what happens when it forwards this packet, right? Because it is a broadcast, the switch receives it, and this is a typical broadcast packet. If you remember, we had discussed different types of layer 2 traffic, right? One was a broadcast, where I said the destination MAC is specifically mentioned as a broadcast MAC address, which is FFFF, and that is what is seen here in this case. So the broadcast MAC address is FFF, and what happens? It is sent to all the PCs. Now what happens here is that all the PCs now know about PC1's MAC address. Okay, because they received the GR, right? So now what happened is they knew they received a packet. They received a packet from this IP address with a source MAC of this address. So now what happened? Now they will also make an entry in their ARC table. For this source IP, this is the MAC address. Similarly, PC3 would know about PC1's MAC address. PC4 would also know about PC1's MAC address. Everyone would know about PC1's MAC address. So what happens the next time when I'm trying to ping any PC, ARP will not be generated. ARP will never be generated. Okay, so that's what happens here. So similarly, let me assign IP addresses to all the other PCs. And whenever I do so, all the PCs will generate their own GR. Any question with GR? Because it is another interview question. What are the different types of ARPs? Right? You have GR, you have a normal ARP, then you have a reverse ARP, then you have a reverse ARP, then you have a proxy ARP, then you have a GR. What are the differences between these? We'll discuss about ARP and ping at a later session in detail, right? However, because the GR came up in this session, I'm just talking about it. So now, let me just quickly ping 10.0.0.2, okay, just to make sure that everyone receives ping from each of them, 10.0.0.3 and 10. And let's just simply check the MAC address over here. So MAC address table, and we'll see, because all the PCs generated their own MAC addresses, sorry, their GR, we can see the MAC address of switch, the MAC table of the switch is already populated. Okay. So this is PC4, PC3, PC1, PC2, right? All of them there already. So again, I don't think I'll have to do a ping. Let me 10.0.0.4. All right. Anyway, there was no need for a ping because already a GR was created. So all the packets know about each other's, all the PCs know about each other's MAC addresses. So I did not have to create a ping for an ARP request over here. However, to be on a safer side, I just did that. Now, the first part is complete, where all the PCs, they know about each other's MAC address. Right? Now, what we are supposed to do, the switch does not know about anyone's MAC address. Right? So clear MAC address table. Right? Now, if I do a show MAC again, MAC table is completely empty. Right? So just now with GR's example, we saw what a broadcast packet looks like. Okay. Now let's check what a unknown unicast packet looks like. Okay. So ping 10.0.0.2, right? And let me bring that into a simulation mode. Okay. So when I do a ping, okay. Okay, why did it generate an ARP first of all? Why? It already knows about ARP. Now, I don't know why I did it generate in R last time. Anyway, so here if you see the first Ethernet packet, right? Because as we said, all the PCs, they know about each other's MAC address, right? So PC1, it already knows the MAC address of PC2. So the destination MAC is PC2's MAC address, its own source MAC address, right? Then in the IP header field, source IP, destination IP, right? So as we will also discuss about the Ethernet header and the IPv4 header later, right? But just see, this is how the IPv4 header and an Ethernet header looks like. And also see that there is no mention of VLANs in the Ethernet header. There is no mention of VLANs over here. So currently, you can see PCs, another thing, PCs, they do not understand VLANs. So that is why we do not see any VLANs mentioned over here. Now this packet goes to the switch number 1. We know that when the switch number 1 reads the source MAC address, we just discussed in our in our last session that the switch reads the MAC address from the source part, right? So let's check the switch's MAC address table. Oh God, I did a mistake.
Cleared the MAC table.
Yeah. Right. So now let's look at the MAC address table. So it made a note of the MAC address. So it entered fast Ethernet 0/1 interface, right? And it made a note of it that at fast Ethernet 0/1, I have received a data with a MAC address of 01, this MAC address, which is PC1's MAC address, right? Then it checks, does it know about the destination MAC address? Does it know about the destination MAC address in its MAC address table? So we know that there is no other MAC address entry in this table. So obviously what the PC is going to do, this is an unknown unicast packet for it. And we know that an unknown unicast packet is treated like a broadcast packet. Unknown unicast means it's a unicast where there is a source MAC address and a destination MAC address. However, the destination MAC address is not present in the MAC address table of the switch. That is why this is an unknown, but a unicast, right? And an unknown unicast data is treated as a broadcast, right? So you will see the switch will broadcast it out of all the interfaces. And to answer Vivek's question in the last session, the split horizon. Switch did not forward this out of 0/1. That is what split horizon means. The data which I received on the same interface, I will not forward it out back again. That is what split horizon means. And over here, PC3 and PC4, they ignored this packet because the destination MAC address and the destination IP both were not of these two PCs. And hence PC2 accepts it, correct? Now, when PC2 accepts it and it responds, right? So when it responds, let's check what does it respond with. So inbound details, you can see this is the incoming packet with PC2's MAC address and PC2's IP address as the destination. When it is outbound or when it is sending back, we will see this destination MAC is now the source MAC, right? This is PC2's MAC address and this is PC1's MAC address. Destination IP is PC1's MAC address, right? Now PC2 responds, it reaches the switch. Switch reads the source MAC address and makes an entry. So it read the source MAC address and it made an entry. Then it checks the destination MAC. Does it know how to reach the destination MAC? Yes. How it should, if it wants to read this destination MAC, how it should forward the data? It should forward the data out of 0/1. And that is what switch will do. It will forward it to PC number 1 via 0/1. In this case, there was no need for a broadcast because it is a unicast. The MAC address, the destination MAC address is not neither a broadcast MAC address with all Fs, nor it is a unknown MAC address where the destination MAC address is not known by the switch. The switch knows it, and hence it forwards the data to PC number 1. Okay. Now, if we see this same thing, if I do a ping of PC1 to, let's say, PC number 4, we would again see a broadcast. Let's check that. Because PC4's MAC address is not known by the switch. I'm not sure why it keeps generating an R. Okay, anyway, let's see with R. Right. So it's a broadcast. It reaches all the PCs. Right, PC2 and PC3 do not accept the packet because the destination IP is not of PC2 and PC3. It is for PC4, 10.0.0.4. Let's check the ARP. Okay, so you will see it is an ARP packet, right, with a destination MAC of FFFF. Source is this, and ARP has a source MAC entry also. It has a source IP entry also. It has a target MAC entry also, and a target IP. Target IP or the destination IP is 10.0.0.4, and that is what PC4 accepts it. Right. Now, a similar case we would have seen when the first ping packet would have generated. PC1 sends the packet with a MAC address of PC number 4. But the switch would not know the MAC address of PC number 4, and hence it would broadcast it. Similarly, PC2 and PC3 would ignore it. It would be accepted by PC number 4. Right. Now, when PC number 4 responds, okay, switch number 4, sorry, the switch accepts it, checks the source MAC address, makes an entry. Show MAC address table, it made an entry, 0/4, right? It made an entry with the source MAC address. Then it checks, does it know the destination MAC address? The destination MAC address over here, you can see, is given, right? And DD41, right? DD41 is the destination MAC address. DD41 is present, and it should be sent out of 0/1, and the switch forwards it to PC number. But this was an ARP. Now the actual ping comes. We will see the ping being sent, but this time it's going to be unicast because ARP was generated and the switch already knows the MAC addresses of 3 PCs. It does not yet know the MAC address of PC number 3. It would know the MAC address of PC number 3 in a similar fashion. So with this, we saw what is a broadcast, what is a unicast, and what is an unknown unicast, and how the switch treats it. Okay. Now, another interesting thing, but before I move on, any question, or do you want to ask any scenario, or do you have any question in mind that you would like to check here? All right. Now, let me remove this PC. And now we will also see the same thing if I do a like uh, what do you say, packet flow. Okay, let me just quickly go through the packet flow, not through the practical, just showing you through a diagram. Okay, so let's say I do a ping, right, from on PC number 1 to 10.0.0.6. Again, assuming all the PCs, they know about each other's MAC address, and the switches, they do not know about each other's. The switches do not know about the MAC address, right? So the packet reaches switch number 0. This is switch number 0, and this is switch number 1. So it reaches switch number 0, right? And it checks for the MAC address of 10.0.0.6 or PC number 6 MAC address, and it does not find in its MAC address table. So it makes a note of the source MAC address and the port, and it forwards or broadcasts it out of all the interfaces, right? This packet reaches switch number 1 as well. Switch number 1 makes a note of the source MAC in its MAC address table, then checks for the destination MAC. And the destination MAC is not found in the MAC address table, and it will broadcast it out of all the interfaces. Correct? Now, the only device that could accept this packet is PC number 6, because that is what we have pinged. So PC number 6 accepts this packet. When PC 6 responds, right, the switch makes a note of it, makes an entry for PC number 6 MAC address table. Then it looks for the destination MAC. Destination MAC is 10.0.0.1. Because 10.0.0.1 or the MAC address of PC number 1 is already in the MAC address table of switch number 1, it forwards it to switch number 0. Switch number 0 also does the same thing. It checks the destination MAC and finds it in its MAC address table and forwards it to PC number 1. I hope there is no question or problem understanding this part with two switches.
No, all good here.
All good? Yeah.
Alex,
Yeah,
can you
Srinivas.
repeat it once? Like second port from reverse port.
Reverse part. Okay. So when PC6 is responding, right, the source IP is 10.6, destination IP is 10.1, right? Switch one's MAC address table already has the entry for 10.1's MAC address with the port number as 0/1. Correct? This switch's
Yes.
MAC address table will also have an entry, right, with 10.1's MAC address and again 0/1. Right? So the packet is received by the switch. Switch makes an entry with 10.6 MAC address and port number as 0/3. Then it checks the destination MAC for 10.1. It finds the destination MAC in the MAC address table and it forwards it out of 0/1. Right? It is received by switch number 0. Switch number 0 makes an entry for the MAC address and the port number, checks the destination MAC and forwards it to PC number 1. Okay.
Yeah.
Now, let's introduce VLANs to this equation. Okay. So, instead of 3 PCs, let me move these pieces. So we all know that by default, when we do a show VLAN in Cisco switches, right, we would see that all the interfaces are already a part of VLAN number 1 by default. This is the default VLAN. Since I think I have worked with only one other vendor, that is Sienna. So, and I am assuming in all the other vendors also, VLAN 1 is the default way. I hope so. Okay. Can someone confirm? Has anyone worked with any other vendors?
Yeah, Lakshan Calyx also it's one only.
One. Okay. So VLAN 1 is the default VLAN, and you can see all the interfaces of this switch are part of VLAN number 1. Okay. So let's go back to our question there. Okay. So let me use just one PC for now and one interface for now. I'll configure PC number 1 interface as part of VLAN number 1. Right. So configuration terminal, interface fast Ethernet 0/1, switch port, access VLAN 10, right? And fast Ethernet 0/3. Ignore PC4 for now. Ignore PC4 for now, right? Interface fast Ethernet 0/3. Okay. Switch port, access VLAN 10. Okay. Switch 1. Is the CLI font okay? Large enough?
Yes.
Configuration terminal. Okay, thanks. Configuration terminal, interface fast 0/3. Switch port, access VLAN 20, and interface fast Ethernet 0/1. Switch port, access VLAN 20. So ignore the PCs that are at the bottom, PC4 and PC5. Okay, we are concentrating only on PC1 and PC6. Right. So here now the condition is, this is VLAN number 10, VLAN number 10, VLAN number 20, VLAN number 20. Okay. This is the situation now. We'll wait for these two interfaces to turn green. All right. Now let's ping PC1 and PC6. Okay. And you can see we are receiving a response. Okay. Now let's check that via simulation. So PC1 creates a packet, and we can see PC1 has all the details already. The destination MAC for PC number 6, source MAC PC number 1, right? And an IPv4 packet with a source IP, destination IP, and an ICMP header inside the IPv4 header, right? Again, as I said, if you notice, there is no mention of VLANs over here. There's no mention of VLANs over here. Okay, because as I said, PCs do not understand all the VLANs. They do not understand spanning tree protocol. They do not understand OSPF or whatever routing protocols you can think of. PCs do not understand it. Any end device, it can be a server, printer, IPTV, or a PC, or even an IP phone, anything, even your mobile phone. They do not understand these protocols. Okay, it is understood only by the networking devices or the devices which are helping to forward the data, not an end device. All right. Now this packet is received by switch. Now when the switch receives it, it knows that it has received a data which is part of VLAN number 10 on an interface which is part of VLAN number 10. Right. Now it opens the packet. It says, I have received a data which I need to forward to this destination MAC. Okay, which is 7888. And it opens its MAC address table. Show MAC address table. Right. 7888. 7888, it already has an entry. That means it knows how to reach, meaning it's a unicast. Now it checks the receiving interface, that is 0/1, and the exit interface or the destination MAC where it needs to forward and the destination port, are they from the same VLAN? Yes, they are part of the same VLAN, right? So this check is okay. The receiving interface and the outgoing interface, both are part of the same VLAN. So it's okay. I can forward the data. Now let's open the packet here itself. And this is the input data, incoming data. You can see there is no mention of VLANs over here. Let's check the exit data as well. In the exit data also, there is no mention of VLAN ID over here. So what is happening? The PC is basically sending the data without any tagging. That is because we have configured this interface as an access VLAN. Access VLAN meaning only one VLAN or VLAN data can enter or go out of it. So there is no point for the switch to tag it with that particular VLAN. All right. Now it forwards the data. Switch number one accepts it. Why? Because there is no VLAN tagging, as we saw. The input data, you can see there is no VLAN tagging. When there is no VLAN tagging involved, the switch assumes that the data that it is receiving is part of VLAN number 20, and hence it accepts it, right? Then it checks the MAC address table, looks for the destination MAC address, checks if the receiving interface and the outgoing interface are part of the same VLAN, and forwards it to PC number 6. PC number 6 also responds back, switch number 1 accepts it, checks that the receiving interface is part of VLAN number 20. Right, 0/3. Receiving interface is part of VLAN number 20, right? And PC1's MAC address and the outgoing interface is also part of VLAN number 20. So this match is okay, meaning I can forward the data. And why am I able to forward that data? The reason is because I have configured it as an access VLAN. There is no mention of VLAN ID over here. And it forwards the data without any VLAN tagging. Switch 0 accepts it because it does not see any VLAN and forwards the data to PC number 1. Okay, so this is what we just saw with this question. And any other question related to this kind of scenario? If you understand this logic, what is access port, what is trunk port, you can answer any question related. Okay. In the last class, we saw some ridiculous question where the interviewer said, if you connect it back to back, what will happen? It is a ridiculous question. However, you can answer that. What is going to happen? Right? This is 10 and this was 20, right? And if you connect it like back to back, this is also VLAN number 10. This is VLAN 20. What is going to happen? Right? This was the question, and you can answer it easily when you do a ping from PC1 to PC2. Right? So the switch reads the MAC address. It will broadcast it, provided it does not know the MAC address. It will broadcast it. Right? When it broadcasts, it will obviously go out of this interface, will be received on this interface. Since both the interfaces are access ports, there is no VLAN tagging. Because there is no VLAN tagging, this loop traffic will be accepted by will be accepted by this interface, and it will be forwarded to PC number 2. It is a stupid question, but even such stupid questions can be answered if you know the logic behind it. Clear? Got the point over here? Any question?
Yeah, I think the same question 2 years back someone asked me, but at that time I was not able to answer this.
Yeah, that's what I was saying. I think you had put this question in the last session. Right. Okay, so coming back to our discussion where tagging will happen. Okay, so let me introduce a few VLANs and change the configuration. And how am I going to change that? I'm going to make this as 10, this as 20, this as 10, and this as 20. Okay. Or this is already, PC number 6 is already 20. 20, 10, 10. This is what I'm going to do. So I'll have to make few changes. Let me do that. So on switch number 0, configuration terminal, interface fast Ethernet 0/4, switch port, access, VLAN 20. Okay. Now on interface fast Ethernet 0/3, we'll have to make few changes because now we are introducing trunk. Now, when we are introducing trunk, what is going to happen? We'll see. Switch port, mode, trunk, right? Then switch port, trunk, allowed VLAN. Okay, I can allow all VLANs or I can allow only 10 and 20. I'm just preferring to allow all VLANs. Okay, all VLANs. Now, on switch number 1, we'll make those same changes. Configuration terminal, interface fast Ethernet 0/4, switch port, access, VLAN 10. Then interface fast Ethernet 0/1, switch port, mode, trunk, switch port, trunk allowed, VLAN, all. Switch port, trunk allowed, VLAN, all. So the interfaces are up. Let's do a small ping. Ping 10.0.0.
I think you put the wrong VLAN. On switch number 0.
Zero slash 4.
4 10 to 10.
4 is 10 only. It's okay.
Oh, on switch number 0, you did reverse.
Let's
Like
show interfaces. Passing 110.20, 110.20.
yeah, here, yeah, here. VLAN 20 is a part of 0/1.
10 to the 10, I think it is.
Okay. Yeah. Configuration terminal, interface, passing 0/1. No switch port, access, VLAN 20. Port access 10. Then interface fast Ethernet 0/4, switch port access. So if you ping now, we should see a response. Okay. And if we try to ping some other, let's PC number 6, we would see a request timed out. Okay. Now let's go to the simulation mode and check what is actually happening. So when I do a ping of 10.5, okay, packet is generated. Okay. Again, we will see there is no mention of VLAN ID, destination MAC of PC number 5, source MAC of PC number 1, right? Destination IP 10.0.0.5, 10.0.0.1 is the source IP. It forwards the data to switch number 0. Switch number 0 accepts it, right? Switch number 0 accepts it. It makes an entry. I'm not opening the MAC address table. We already know that part. Inbound detail, again, because it's a receiving packet, we are not seeing any VLAN ID mentioned here. But because now we have created a trunk, the moment we create any interface as trunk, and if the data is flowing out of the trunk interface, we will see a VLAN ID mentioned here. TCI, tag control identifier. TCI, you can see this is 000A. Now, can someone tell me why is this A?
A is
Is
VLAN
the
10,
10, right? A means
hexadecimal.
hexadecimal.
Correct. It's the hexadecimal for 10. Okay, A is the hexadecimal for 10. So whenever you open the Ethernet packet, you will see the hexadecimal value, and this is for VLAN number 10, right? As I said, with this, what is happening? Switch 0 is tagging it with VLAN number 10. And why is it tagging? Because when we open the show trunk interfaces command, show interfaces trunk, we would see on this interface, it allows 1 to 1005 VLANs. All the VLANs are allowed. But now what is happening? The receiving interface is part of VLAN number 10. And the outgoing interface, since the outgoing interface can send all the data from 1 to 10005, it is tagging it with VLAN number 10. Again, why is it tagging it VLAN number 10? Because the receiving interface is part of VLAN number 10. Okay, so the tagging also depends on the receiving interface's VLAN ID. Okay, so here, because the receiving interface is part of VLAN number 10, the outgoing packet or data also has a tag of VLAN number 10. So we can see VLAN number 10. And this data is forwarded to switch number 1. And again, on switch number 1, because it can accept, again, it can accept all the VLANs between 1 to 1005. It accepts the VLAN ID with VLAN number 10. VLAN number 10. Okay. And it will forward it to PC number 5. Again, as I said, PCs do not understand VLAN. So when the switch is sending this data to PC number 5, check the outbound data. It removes the VLAN ID. It completely removes that VLAN tag. So please remember, the VLAN tag is added by the switch, not by the PC. Okay, some interviewers may question you, will PCs add VLAN? No, they do not understand VLANs. Only switch, because switch will add it, switch will remove it. And here again, the switch removes the VLAN ID, forwards it to PC number 5. PC number 5 will send it back. When it sends back, we will see there is no mention of VLAN ID. No mention of VLAN ID. But when switch is forwarding it, it will add the VLAN 10 ID over here and forwards the data to switch 0. Switch 0 checks the VLAN ID, checks its MAC address table, and forwards it to PC number 1. All right. Similar thing would happen with switch PC4 and PC6 as well. If you ping PC number 4, sorry, PC number 6, ping 10.0.0.6. Switch 0 receives it. It checks the incoming interface is part of VLAN number 20, and that is why it is supposed to add VLAN number 20 when it is forwarding the data out of trunk interface. So we'd see this as 14. Okay, and if someone is wondering how is that 14 and why is that 40? Okay, 14, this is a hexadecimal format, right? 1 in its hexa binary format, 4-digit binary format, we write as 0001, and 4 0 triple 1 1 triple 0 1 triple 0. Okay, so 1 triple 0 is, oh sorry, not 1 triple 0, 0 1 0. I'm sorry, I'm extreme. 0 0 0 1 1 0 1 1 1 0 0 1 0 0. Okay, so 1 you write in the binary format as 0001, 4 as 0100. If you convert it into a decimal format, okay, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, right? So 2 power 4 plus 2 power 2, right? 16 plus 4 gives us 20. So 14 is the hexadecimal format for VLAN number 20. That is why you will see as 14 over here, right? And with VLAN number 20, it forwards the data to switch number 1. Switch number 1 reads the VLAN tag of 20. Okay, checks its MAC address table for interfaces which are part of VLAN number 20, forwards it to PC number 6. PC6 responds, switch 1 accepts it, tags it with VLAN 20, forwards it to switch 0, switch 0 checks its MAC address table, forwards it to PC number 4. Right. So when you have trunk, the moment you configure trunk on an interface, okay, you will start seeing taggings over there. You will start seeing tagging. Okay. So now one more thing. Interviewer may ask, what if I add another PC and I do not make any changes? Over here, let's say the interview says I configured it for access VLAN 10, here 20. This is trunk interface, trunk interface, trunk interface. All VLANs allowed. This is 10, this is 20. Now I'm adding I'm adding two PCs like this here also, and I'm not making any changes. I just simply added them, and I'm assigning IP addresses to them. 10.0.0.1, so not 1, 8, 8, and 10.0.0.9, 10.0.0.9. Okay. Now my question to you guys is, if I ping PC8 to PC9, okay, will there be any tags or not?
No.
Because
Okay, anyone else? Anyone else?
yes,
Yeah,
it will not add tag because native VLAN is here VLAN 1, so it will not
correct,
be tagged.
correct. So when I ping, let me take that in this image. So when I ping 10.0.0.9, okay, switch 0 accepts it, VLAN 1, okay. As I said, by default, all the interfaces of a switch are part of VLAN number 1. And if you see, show interfaces trunk, it says the native VLAN is 1. What is the meaning of native VLAN? When you configure trunk interface on a switch, native VLAN acts as access ports or access VLAN, meaning that VLANs, sorry, data which enters VLAN number 1 interfaces like this. This interface, what is that? Is it 0 slash? Yeah, it's 0/2. Okay, 0/2. 0/2 is part of VLAN number 1, which is a native VLAN. So on the trunk interface, when VLAN number 1 is being forwarded, it will not be forwarded with any VLAN tagging. You can see here, there is no tag of VLAN interface or VLAN ID on the exit side, right? And the data is forwarded to switch number 1. Switch number 1 accepts it because on 0/1, again, we said show interfaces trunk. The native VLAN is 1. So it accepts the data without any VLAN tagging, assuming it's part of VLAN number 1, and it forwards the data to that interface, which is also part of VLAN number 1, where PC9 is connected. Okay. Now, second question that they may ask, let me change the native VLAN on trunk interface. Let's say configuration terminal interface fastnet 0/3 switch port trunk native VLAN 10. Okay. And now switch number 1 as well 0/1. Configuration terminal fastnet 0/1 switch port trunk interface fastnet 0/1 switch port trunk native VLAN 10. Now, when I ping from PC8 to PC9, what is going to happen? When I ping from PC8 to PC9, what will happen? Will we see any tagging or not?
I think it will add tag because we configured on that particular interface native VLAN as 10, so I think it will add tag.
Okay. Anyone uh, who agrees with Srinivas or who disagrees with Srinivas? Anyone? Okay, so let's see. Right. So PC sends it, which receives it. Let's open the packet. Inbound, no data, no VLAN ID because PCs do not understand VLAN. Outbound side, on the trunk interface, where on the trunk interface we have configured native VLAN as 10. See here. Now you have a VLAN ID of 1. Now you have a VLAN ID of 1. Why? Because we changed the native VLAN to 10. So any other VLAN other than 10 will be tagged. So the meaning of native VLAN means any other data other than the native VLAN will be tagged. Okay, so here PC 8 or 0/2 is part of VLAN number 1. So when the data is being sent out of the trunk interface, where the native VLAN is not 1, but something else, it gets tagged with VLAN number 1. It gets forwarded to switch number 1. Switch number 1 forwards to PC number 9. Okay. Now let's check what will happen if PC1 sends the data to PC number 5 with VLAN 10. They both are part of VLAN number 10, right? So switch 0 receives it. Let's open the data. Inbound, no VLAN ID. Outbound, also no VLAN ID. As I said, we have configured on the trunk interface the native VLAN as VLAN number 10. And hence, any data that is entering the interface where VLAN 10 is connected, it will not be tagged. No tagging will happen. So the concept of native VLAN means that particular VLAN ID is not going to be tagged. Okay. So I hope what is trunk, what is access port, what is VLAN tagging, everything is clear. Any question? And I think with this understanding, if any other question is asked to you in the interview, you can easily answer.
Yeah. So Laksh, can you hear me?
Yeah.
So here in this case, PC8 and PC9, which are a part of VLAN 1, right? And we have configured VLAN 10 as a native VLAN. So
Yeah.
that is for untagged traffic. So in this case, PC8 and PC1 will ping to each other, right? Because that is a part of VLAN 1 and VLAN 1 is tagged right now.
VLAN 1 is tagged because we have changed the native VLAN feature over here.
Yeah. So in case this PC8 and PC9 will ping, right?
Yeah. They'll ping. Yeah.
Okay.
PC8, PC9.
Yeah.
But
Got it.
what will happen in between when switch 0 is sending the data to switch 1, it will tag it with VLAN number 1.
Yeah, got it. Yeah. So, beside like, what is the actual use of native VLAN? One I got to know, right? When we want to send untagged traffic between the switches, then in that case we can use native VLAN, right? But what are other use case, right? Why we will connect our PC in native VLAN?
Okay. First of all, that is
Can
how
I
the
tell
switch.
one more? Can I tell one reason?
Yeah.
Laksh.
Please go ahead. Yeah.
Prashant, we can use the native VLAN when we have something like you have a IP phone along with the PC, right? So in that case, so on the same interface, we'll connect IP phone as well as PC. So in that case, what we'll do means we will create one native VLAN on that particular interface. So in that case also it will be useful, like so when you are connecting IP phone along with the PC on the same interface. So because the IP phone can understand the tagging actually.
Okay. What I understood, when we are connecting IP phones and PC, right, all together, so we create two types of VLAN, right? What I understand, voice VLAN and data VLAN.
Yes.
The name is just a voice, but
Yeah.
you give a number to that voice VLAN, and you call it a voice VLAN.
Yeah. So we create two VLAN in that case, but
So let's say
both are untagged or tagged. I don't understand in that case.
Yeah.
Yeah.
See, it is your data sheet. In your data sheet, you say that for voice VLAN, you would give, let's say, from 1 to 10. These are the voice VLANs. Okay. In your data sheet. And then you say let's say for video VLANs. For video, you would use VLANs from 11 to 20. Okay. And any other VLANs or any other traffic can use any other VLAN. Let's say they use 30. What you can do over here is, okay, it is recommended by, first of all, the switches have been designed like that where they need a native VLAN. on a trunk interface, you're supposed to configure a native VLAN. Now it's up to you to leave that native VLAN to 1, or you configure it to any other VLAN. Right. Now, what I have seen is you configure a native VLAN other than 1, let's say for VLAN number 30. Okay. You are running a company where you know that your voice traffic and video traffic are less. So you give them these VLANs and separate them or separate their broadcast room. Correct. Now, instead of using VLAN number 1, you use VLAN 30 for any other traffic. Any other traffic, internet traffic or a broadband traffic or whatever. Right. So you configure VLAN 30 as native because tagging also uses the switch's processing. You need the switch receives it, switch will see that it is part of VLAN number 30, or let's say the switch receives it, sees that it is part of VLAN number 1, tags it with VLAN number 1. So it needs to do a lot of processing. First of all, it is stripping the packet when it is reading. Then when it is again creating the packet, it needs to add the VLAN, adding the header, adding the IPv4 header, everything. Again, the processing is a bit increasing. So what you do, you leave those traffic where a lot of traffic is incoming. You put that into a native VLAN set. It can be a native VLAN 1, the default VLAN, or you choose any other VLAN by yourself. So what is happening? The processing for those data on the native VLAN is not used. It checks the incoming interface is part of VLAN number 30, for example, that is the native VLAN. So the outgoing interface, the traffic which is going through this trunk interface, there is no need for the switch to add a VLAN to it. It can just simply pass the traffic. So this is one real-time analysis that I had done, where the process to decrease the processing, you use the native VLAN.
Yeah.
And mostly it is recommended that whenever you are connecting two switches together, always use a trunk interface. It is always recommended to use a trunk interface. The end, if the interfaces are connecting end devices like this, right? Let's say this is a PC, this is a printer, right? This is an IP phone. There is no need for a VLAN tagging. You can create them as access. But if it is between the switches, trunk is always preferred.
Yeah.
Any other question? Anyone? Vivek, Krishan?
Yeah.
Yeah, Krishan.
Yeah. Next, can you repeat access port?
Access port means there can be only one VLAN. It can be any VLAN between 1 to 4096. It can be any VLAN. Okay. So the meaning of access VLAN is that only that particular VLAN data would exit or will have an entry. And that is why the switches do not tag them with one VLAN. Because I just gave an example of the house, right? Let's say you are living in a house, okay, and you recruited a security guard. Okay, he is looking after your house, and you are the only person living in that house. Let's say you are VLAN number 10, and the security guard knows you are the only person who enters the house and who exits the house. So what is the point of the security guard to check you? Correct. The same concept is done by the switch. When you have configured this interface as access interface with any VLAN, okay, it can be any VLAN. For example, it is 10. It knows that only in VLAN 10 data or VLAN 10 data can enter or VLAN 10 data can exit. There is no need for me to tag it. No tagging will be done in an access port.
Okay.
But let's say you are living in an apartment and the same security guard is standing there. Now there are a lot of people who will enter and a lot of people who will exit. So he needs to check them, right? That is a similar concept of trunk.
Okay.
When it is trunking, when you have a trunk interface, the switch will tag with VLAN. Tag with a VLAN. So that when it is sending the data, the next switch, whoever is receiving that data, can read this VLAN or can do a check. Similarly, when switch number 1 is sending that data, it will add a VLAN so that switch 0 can understand which VLAN does it belong. Then, but when switches are forwarding to, or when the switches are forwarding the data out of an access interface, they will not tag it. Right. So this is VLAN number 10. This interface is VLAN number 10. When the data is received, it knows that the interface is VLAN number 10. Right. When it forwards it, it will tag it with VLAN number 10. Switch number 1 will accept it, and switch number 1 will forward it to PC5. But switch number 1 will not tag it. No tagging of VLAN number 10 because it is an access interface. Okay, let's assume that if this interface is also a trunk interface, for example, another scenario question from an interview point. This interface is a trunk interface. Will the switch tag? Yes, it will tag. It will tag. The receiving interface or the data, right? This interface was VLAN 10, so it tagged it with VLAN 10 here. So switch 1 is receiving a data with a VLAN number 10. So when the data is being forwarded to PC number 5, it will add a VLAN 10 over here. But anyhow, the PC will not understand VLAN number 10. It will not understand VLAN number 10. So this is the difference between access port and trunk port. Access port, no VLAN tagging. Trunk port, there will be tagging. And in a trunk port, native VLANs are not tagged. It can be any native VLAN. Native VLANs are untagged. Remember this. So native VLAN are equal to access VLANs. Clear?
Yeah, clear.
Any other question, or does anyone has any other scenarios that they can come up? All right. So I'll stop recording here.